let me take over. And as I said, in terms of the agenda, I will talk a little bit about CAD modeling of the different geometries that were investigated during this project with our tool cases, and to kind of explain a little bit where this fits in. If you're not familiar, many might be. Cases is a design and optimization platform that comprises three main components. The ones in blue here, automation, that's coupling to external simulation codes, and optimization is the optimization environment where you can run optimizations and post-process results and so on. But today we will focus on the first component of cases, which is the CAD environment. And cases is basically a very specialized CAD tool with a focus on geometry variation specifically. So something that with many traditional CAD tools is rather difficult to do. We want to be able to change geometries in a very flexible and robust way during the optimization process. And for that we have this specialized environment with a focus on these things: robustness, smart parametrization of the geometry, simulation-ready geometry that can be provided directly to the next step in the process, and so on. And if we look specifically at turbomachinery design, because here within the project Gamma we're mainly talking about turbomachinery development, there we have a dedicated set of capabilities within cases specifically for turbomachinery design. There is comprehensive blade and volute modeling. You can include not only these bladed geometries or the casings, but also all kinds of other flow structures like bypasses, wastegates, cooling structures, as you see here for the axial blade, but also other parts that come upstream or downstream of your turbo machine, like ducts and things like that. So in general, cases is not only a turbo machinery tool, but a general purpose tool. So yeah, we have a very high level of customization for the development of these geometries. So there are no black box models where you can just select a certain type and enter your parameters, but you can really create everything by yourself, fully customized as a user. I mentioned this already. There is a focus on high robustness and flexibility to change the geometry, consideration of manufacturing or packaging constraints. You can analyze imported data that come from another CAD system, from a preliminary design system, or from even a geometry scan, and extract parameters from this data, or fit an existing parametric model to these imported data. Alternatively to generating a parametric model of these geometries, you can also use morphing functionality. We see it in the picture here at the lower right, where we have an imported geometry and the blades are being morphed by an RBF-based approach. And yeah, Cases also has a full scripting or programming environment, so you can also write your own customized preliminary design methods and include them in the process. This is just a quick view of the user interface to give you an idea how it looks, and yeah, just a few different turbomachinery applications. Of course, turbochargers, which is what we're talking about today, but also gas and steam turbines, propellers, fans and blowers, pumps, and hydro turbines. Okay, so much for a quick introduction, what we're using and in which environment we're doing the following steps now. And now let's come back to the R&D project Gamma and what we've done in terms of CAD modeling. Here on this picture, on our slide, you can see the different components that we worked on and that were modeled within cases. So we have on the compressor side the volute and the compressor wheel with the bladed diffuser, and on the turbine side we have the turbine wheel. The aims of the parametric models that we created here were first of all to implement the theoretical parametrizations that were provided to us within this project by MTU, or sorry, Rolls-Royce Solutions, sorry, as well as TU Darmstadt. So they came up with certain ideas and parameters that they wanted to use in the models and so on. And we basically used that as an input to implement the actual models. Of course, within the models, we also took consideration of manufacturing constraints. We'll talk a little bit more about that later on, and the experience in terms of manufacturing, but also other disciplines that was existing at Rolls-Royce Solutions. Of course, we want a high degree of flexibility in those models so that we're able to cover a large design space, as large as possible, and we want the models to be robust so that we can do a very reliable variation of the geometry within the optimization process. So let's start now with the compressor side of the turbocharger and take a look at some of the geometry characteristics. So the blade design was intended to have flank millable blade sides. That's why we use these rulings. I'll mention something more later on. And there is the option to include a curved leading edge within the blade, which would require a different type of cutter for milling. If we have a straight leading edge, then we have a completely flank millable blade. Then, as was mentioned by Fritz already, we have a vaned diffuser, which with parametric vanes, and the kind of special thing here was that the shape of these vanes can change in circumferential direction, so they don't necessarily have to be all the same. The geometry export here for CFD for the blade shape was exported in Geom Turbo format, and for structural mechanics we created a solid CAD segment that was exported in a CAD format. So if we look at the volute, we have a simple cross section which is made up of circular segments, and we had some constraints on the maximum outer radius and on the height of the volute. Regarding the meshing, we also included support structure for the blocking of a structured mesh directly within the parametrization of the geometry. I'll give some more details about this later. And we also had the option, at least, to add a ported shroud to the compressor if it's necessary to delay the onset of surge. So let's look at the modeling process for the compressor impeller. So here we start with the meridional contours, hub and shroud contour, and then we specify the blade angle distributions or beta distributions at the hub and at the shroud. And this allows us to create the mean camber lines of the compressor profiles on hub and shroud. And we can connect these two camber lines with a camber surface. And as a next step, we specify the thickness of the profiles and at the hub and at the shroud. and then we can apply this thickness to the two camber lines we had defined before, and then we connect these two profiles at Hub and Shroud with these so-called rulings, which are intended to guarantee the flank millability, if that's a word, of the blade. And then we fit in between these two sides. They are extended past the leading edge, and then between these two blade sides we fit the leading edge shape. And as I said, here we see a kind of curved leading edge, which wouldn't be flank millable, but it can also be straight. And that will give us our main blade surface as well as the splitter blade, which is basically modeled in the same way as we've seen here in the process. Then as a second component on the compressor side, we have the vane diffuser. As I mentioned here, we have an individual parametric surface for each of the vanes, but they are generated in an automated loop, and we can change the parameters of the vane. We can change the what they call the airfoil parameters in spanwise direction, height direction here, but we can also change the shape of these vanes in circumferential direction to possibly take into account asymmetries or in the flow that are due to the volute being non-axisymmetric and things like that. And the inputs are either distribution functions for certain parameter values, which basically describe how a certain parameter of the vane changes in circumferential direction, which will then give us differently shaped vanes. Or, of course, these values can also be constant, and then at least that parameter is the same for all the vanes. And finally, the last component on the compressor side, the volute. As I mentioned before, we have a cross-section here that is modeled with circular segments. You can see it here on the right side. And the main kind of parameters that are being changed here are the so-called board angle. You can see in the very in the bottom left in the animation, you can see the change of this board angle. And we can also change the distribution of the A/R ratio in the circumference of the volute. So if you're not familiar, A is the cross-sectional area, which is highlighted in gray here, and R is the centroid radius of this area. And as you see here in the diagram, we can set up a distribution function that describe how this A/R ratio changes when going around the volute scroll. As I mentioned, we have some space constraints regarding the maximum radius and the height. So you can see in the animation here in the middle, if we reach the constraint for the maximum radius, the cross section, if we increase the area, starts growing in vertical direction. And basically we hit the constraint and stop there and then grow in vertical direction. And if we reach the maximum height, which is the other constraint, then the cross section starts moving inward, or starts growing inward, basically. The very critical area in the volute is the so-called tongue, or cutwater, or whatever you want to call it, where the scroll basically self-intersects itself or intersects the outlet diffuser, and that tongue is modeled with a custom fillet surface, which has the advantages of having a very good and clean representation, being very robust when we change the shape, of the volute, as you can see here in the animation. Yeah, and having a very good quality of the overall solid that we export, because obviously for meshing and so on later on, we don't want to have open edges or intersecting faces and so on. That would kind of throw stones in our meshing process. And then within the parametric model for the volute, we have included some preparation for the meshing process. It's actually for geometries like these volutes, it's quite difficult to create a robust structured meshing, especially when we're changing the shape very flexibly. And the idea here was that we create a support geometry for the blocking of the structured mesh directly within cases inside of the parametric model. So basically, the support geometry is coupled to our geometry directly, and if we change the geometry, we also can adjust these block boundaries very nicely, and then we can export the boundary curves to IgG for the meshing process, which we'll hear more about from Numeka. Yeah, and that's about the meshing. And finally, on the compressor side, we had 59 parameters that were used for optimization purposes, which basically are related to the shape of a hub and shroud contour, obviously blade parameters that control the blade shape, and as well as the diffuser vane, the impeller back as well that we don't see here, which is maybe not aerodynamically interesting, but for structural reasons, and of course the shape of the volute. So if we move over to the turbine side and look at some of the characteristics of the geometry that we developed there. So we have so-called radially fibered blades, which means that all points on the blade camber surface are dependent on the hub streamline. So as you can see in the picture, we have our hub camber line on the hub, and then basically going from the axis of rotation, if we extend radially outward through our hub camber line, we obtain the camber surface. And that's structurally beneficial because basically it aligns the fiber of the blade with the centrifugal forces. Exactly, that's what I was looking for. And so it's structurally beneficial, but it's also beneficial in terms of the optimization because the shape of the blade is mainly controlled by the hub streamline, and then it reduces the number of design variables of the model. Yeah, we can see also here with the cross sections, airfoil sections applied to the blade, how it looks. There is also the possibility to add some end wall contouring to the hub, which means that or is obtained by changing the hub contour. So if we have our meridional contour for the hub, rather than having a constant contour that is just revolved around the axis of rotation, if we change that in circumferential direction, we can get this contouring on our hub, and that's can be aerodynamically beneficial to influence the flow and maybe secondary flow phenomena at the root of the blades. But it's also beneficial in terms of reducing inertia, so we can take off some material there, and then of course we want to have a turbine with as low inertia as possible so that it revs up quickly and shows a good dynamic behavior. And for the same reason, we can also add these scallops or webbings to the hub. In terms of structural integrity, the fillets at the roots of the blades are also quite important, and it's actually, I mean, not very surprisingly beneficial when the fillet radius between the blades or at the bottom of the blades is as large as possible. And here we had included in the model an automated routine that basically calculates the maximum fillet radius automatically using an internal optimization, and then gives us the result that we want. And in terms of the export, we want to export, again, simulation domains for fluid calculations and structural computations, and they have to fit exactly to each other, so they are also generated directly from within the CAD model and exported. And as we've heard, we also were looking into combinations of axial and radial turbines, and maybe as a side note, also this model or the parametrization was constructed so that within the same model, within the same parametrization, we can also generate the axial variant of the turbine, so to say. So let's look at the blade modeling process for the turbine side. We again start by generating the meridional contours, hub and shroud, as well as the backdisk contour. Then we generate the camber surface by creating a hub camber line. This is described here as a theta over m prime distribution. So theta is the rep angle, and we describe how the rep angle is distributed, and this gives us our camber line on the hub. And then, as I explained before, starting from the axis of rotation, we extend the radial fibers through this hub camber line and generate the camber surface. And then we want to apply our thickness, blade thickness, and for that we have a parametrized cross section that is controlled by a few points along the curve, and then we have values for the width position of these points in radial direction. So you can see, if you look at these parameter distribution graphs, you see obviously we start with high values for thickness at their inner radius, and then we get thinner, and some of those points converge to the same value, so that we just have a constant thickness, and this will give us the blade surface. On the turbine side, we had a total within the model of 70 design variables, and 40 of those were selected for the optimization process. All right, that's it from my side about the CAD parametrization. Now I would like to give over to Thomas Hildebrand from Numeka, who will tell us a bit more about the CFD setup, CFD workflow that was used here. Let me make you the presenter, Thomas, and the floor is yours.
Mattia, many thanks.